Yep. I think they're in my photo gallery.
1 second, 1 second, 1 second. I have an introduction too. Sorry about that.
Oh, okay.
Can you see my screen? Let me share my screen here. Hey, everyone. Welcome to XCamp 2023 February USACO solution discussion. This session is for server level. Today, I will give you a quick introduction about XCamp. My name is Charlie. I'm the co-founder and the principal of XCamp Academy. Then Albert, he will give you the tutorial, the solution sessions. Later, I will give you the class introduction and how to help you to prepare next USACO. XCamp was founded in Silicon Valley 6 years ago by me and my Google colleague Yuan. We provide beginner to master level classes. Our curriculum developed by seasonal coaches, including IOI medalists, USACO veterans, and other medalists too. We have a proven record. We have a solid knowledge about the data structure and the algorithm. For USACO campus last year, also in the December session, we have 2 students get into the top 10 in the platinum division. We provide beginner lessons to help kids love coding. Then we provide algorithm and data structure to build foundations for you guys to have complete knowledge. Then later on, if you like competitions, some of you, you can continue this direction. Also, some of you might go to academia or industry to be engineers. Now for this session, we have Albert. He's our previous XCamp students. He's also our current silver level instructor. He's in UC Berkeley for his EECS major study. Now, Albert, I'm turning to you now.
All right, let me pull this up. So first problem is about like a bakery or something. So the question basically says, we got, I think it was N, N orders. And then of which of those, each one has AI cookies and BI muffins. And then it takes TC time to cook a cookie. And then TM time to cook a muffin. So, all right, so how are we going to end up doing this? So for a cookie, we would have wait, hold on. Okay, here we go. So if we spend 1 money, and then we would either decrease TC or TM by 1. Right? And then we want to find the least amount of money such that all orders are satisfied. Given that each order will must be completed in time CI. So how do we go at this? So first of all, like our initial intuition is to binary search on X, because, well, if the total money spent, if we cannot satisfy this relation with X dollars, then there is obviously no way to satisfy it with X minus $1. So yes, so obviously we would like this makes us think about binary search on X. But it's really unclear at this stage how we are going to, given X being the amount of money that we spend. So binary searching on X seems like an initial reaction, but since we have both cookies and muffins to deal with, we're not really sure how to use binary search here. Or especially the question is, how are we going to split between cookies and muffins? And the first thing that we would want to do is basically just see like what are our possibilities here. So we would initially want to just go over, this would be way too slow because TC and TM are both less than like 10 to the 9th or something. But let's just first assume that we have like zero cookies and M muffins or something. Time 1 for cookies and time TM for and like TM for muffins. Then all that we can do is like at this stage, if we increase the number of cookies, then if we increase number of time for cookies, we can then decrease the number of time for muffins. So we sort of have like, our graph essentially looks like we have like two extremes, one where we spend everything on cookies and one where we spend everything on muffins. Then in this case, any like case where we can't really satisfy, where the muffins are like the bottleneck, will end up not working. And any cases where, so let's say that we have like a graph of like the amount of time that goes like this, where the y-axis is like the amount of like unfulfilled requests. So then if we spend everything on cookies, everything with regards to muffins will stay the same. So if muffins are our bottleneck, then we are not going to be able to like really do anything to fix the muffins. And similarly, we can argue the same for muffins on the other side and cookies being the bottleneck. There is like some point where like increasing the amount of cookies, amount of time for cookies is going to start harming the orders with muffins as a bottleneck and vice versa. So initially, for cases where like muffins are the bottleneck, we would want to like increase the number of cookies and decrease the number of muffins. And if cookies are the bottleneck, we would want to increase the time for muffins and decrease the time for cookies. And then, so it's sort of like a compromise between these two ends, where some people want cookies to be made faster and some people want muffins to be made faster. So we can essentially look at, so we can first, there are two ways to go forward here. So the first way is to use a ternary search because, well, I mean, I'm not really going to go too much in depth on ternary search, except because I don't think many people really know what ternary search is. But you can search it up and it works in cases where like the answer is sort of unimodal. Like in this case, we have like a bunch of cases where it doesn't work on the C end, and then a bunch of cases where it works, and then a bunch of cases where it doesn't work on the M end over here. So we can sort of use ternary search to find this. This is pretty much as in-depth as I'm going to go for this solution. The better solution, or like the solution that requires less like advanced algorithms, is just binary searching twice over the amount of money you need to remove, binary searching twice over the amount of money you need to reduce TC to something that satisfies all clients with time AI greater than BI. So binary search over the amount of money needed to reduce TC to satisfy everything with AI greater than or equal to BI, because in this case, we see that the cookies are the bottleneck. And then after this, we can binary search over the amount of money needed to reduce TM to satisfy everything else. So like everything with AI less than BI, because in this case, we see that the muffins are the bottleneck. So let's say that this binary search gives us an output of C, and then this binary search gives us an output of M. So then we basically need to check if C plus M in this case is less than or equal to X. And if this is true, then we can basically set like an upper bound on X. And if it's false, then we can set a lower bound. Any questions on this one? Any questions on this one, or are we? Oh wait, there are questions. Okay, so this is a binary search inside of a binary search. Yes. No idea why the Ryan guy said no. I think that's incorrect, because you basically just think about it like you do like, oh no, it's not two different ones. It's a nested binary search. So you have like one big binary search over X, and then inside that you have one for C and then one for M, basically. Yes, the Ryan guy. Next we got problem 2, which I think is the crime one. Yeah. So okay, so the alibi one. So yeah, this one says Farmer John has like G farms, like G vandalized properties. And then he's basically interrogating the cows, and they're like he interrogates his N cows and says, "Hey, I know one of you has been like committing crimes on my property." And then okay, no, we are on silver 2 right now. So this one is like he interrogates his N cow. He's like, "Hey, who did it?" And then he's like, and then the cow's like, "No, I didn't do it. Because I was here instead." So each of them has like an alibi of a specific time. And it basically says, the question is basically which of the N cows so which cows have to be innocent? So basically our input goes as follows. We have like a cow at like 0,0 that is been vandalized at time 100. We have another cow at another land at 50, which has been vandalized at time 200. And then we got a bunch of cows, or where they said they were at certain times. So first, let's start off with the first cow who says he was at 050 at time 50. Which means that he has to have basically been able to go from the previous vandalism slot to the current vandalism slot, and then from the current vandalism slot to the next vandalism slot in the allotted time. So previous vandalism slot does not exist, so we can ignore that. Current vandalism slot to next vandalism slot is 50 to 100, which is this possible? Yes, this is possible because the distance is exactly 50 and he moves it like you move it like 1 meter per second or something. So yes, this first cow is possibly guilty. The second cow is at 1,000, 1,000. So he's way out here. There's no way he could have gone to. And he was at that time he was here at time 0. So once again, there's no previous vandalism spot. So he has to go to the first. He would have to have been able to go from here all the way down here in 100 seconds, but he is way too far to have possibly done that. So he is innocent. The third cow was like, dang, I was literally at the site of the vandalism at the same time that the vandalism happened, which is really stupid. So he's like 50. He was at 50,0 at time 200. Also, I'm really smart and I put this in a terrible position. 0.50 t equals a 50 like this. Yes, and then so our third cow is here. So if our cow has been caught at the same time that a vandalism occurred, you basically just want to make sure that is he at the same position or not? And that's a pretty easy check. And in this case, it returns, I think he's guilty. And the last one, 10-0 at time 170. So this means that he would have had to have been able to travel from 0 to 10-0 in 70 seconds. Makes sense. But you'd also have to have been able to travel from 10 to 50 in 30 seconds, which does not make sense. So 4 is innocent. So this sort of shows us a pattern here where basically what we're doing is we are starting from like the first, we're basically trying to go from the previous to the next. So we check if like the Cartesian distance is like feasible to go from like the previous vandalism spot to the current place. So we would want like, let's say we have like T1, T, and then T2. So we want the distance over here to be equal to like T minus T1, be less than or equal to T minus T1, and then the distance for over here, this distance would have to be less than or equal to T2 minus T. So we just need to make sure that both of these are satisfied. We can find whether or not where T belongs within like our list of vandalism spots with a binary search tree. For each cow. So we basically just store all of our points in a binary search tree sorted by time, and then we basically just use like lower bound or whatever to find which cow it's after or something. And if it turns out that we're at the beginning, we don't. If T1 doesn't exist, we can ignore it, and if T2 doesn't exist, we can also ignore it and just consider one of the two relationships that we have. And the final case is if like T equals to something, then what we would have is essentially just check if locations are same. And yeah, this is just it. And yes, distance is the Euclidean or Cartesian or Pythagorean distance. If you used Manhattan distance on this problem, I am paying my respects. Very unfortunate. But yeah, that's basically it for this problem. This one's like a simpler one. Finally, last problem. Problem 3 is a graph one. Yay, this is fun. Woohoo, everyone loves graphs. If I was everyone, everyone would love graphs. Anyways, we got n vertices, m edges. And then what's cool about these edges is that like you have like a start position C and then like end position D, right? Oh, for problem 2, how could you have told it was Euclidean distance? It says somewhere over here, like it never said anything specific about like Manhattan distance, and for this problem it was really confusing and hard to tell. Yeah, it's really difficult to tell, but I think you're supposed to just assume that that's the case. Yeah, no, the cow at 050 does arrive just in time. So like it could be man. Honestly, the best way to have figured out was to code both ways, but like usually when they want you to do it in Manhattan distance, they would say like specifically Manhattan distance and not like Euclidean distance. So I think that for the benefit of the doubt, you should assume it's not Manhattan distance. Last problem, n vertices, m edges. You start at position C and you end at position D. So you also have like a start time R and an end time S. So what we're basically saying is that like if we go to a position like a vertice C at time R, then we basically end up at D at time S. So let me draw this graph real quick. And then 2 to 2 again. And then 2 to 3. Okay, and then this is the first part. And then our times would be like 0, 10, and then like 11, 0, and then like 120 or something. Which basically means that if we leave 1 at time 0, then we end up at 2 at time 10. We can also leave 2 at time 11 to go back to time 0 at 2. And then if we leave 2 at time 1, we can go to time 20 or something. So there's also another constraint, which is like the layover time is like AI for each I or something. So each edge we can represent each edge as like C R to ds. So what we do is we can store like all of our edges in an adjacency list and do DFS, right? Except our DFS is going to be slightly different in that we have to use like in that we have to sort our edges by R in decreasing order. I mean, I think we should not really in decreasing order because there is a bit of an implementation thing to deal with here. So we have to sort our orders by R, our edges by R. And then we basically want to take like the edge with largest R each time and try to like basically do DFS from it. So like we basically checked like for the starting node, which edges can we go to? And that pretty much entirely depends on all of the edges thus far that we visited. So like our position depends on like which edge we've taken, what the D value of that edge is, and then what like whether or not like and what edges come afterwards. So like we basically have like a DFS relationship here where we have like DFS at a vertex and a certain time, because note that we can be at the same vertex at different times. So what ends up happening is we basically like we can basically just do like a while loop here, and Q is while like adjacency of D is not empty, we basically go to like the take out the edge with largest R. And by take out, I mean literally remove it. Like literally remove it, because you don't want to go back to the same edge again because you've already like looked through all the possibilities of going through this edge, and there's no need to look over it again. That's just gonna lead to like extra time wasted, which will give you a TLE. So you literally take out the edge with take out the edge, not with length R, but with like starting time. No, I said largest R. I can't read my own handwriting. Largest R. So we literally remove it, and then we see that we now have an edge CRDS here. So we basically just do like we basically just take a graph D, and then we basically just do like DFS at DS, and then we see. Oh wait, no, first we need to check if like R is greater than like T plus A of V or something. This is just because of the layover constraint over here. If not, we can just break. Otherwise we like DFS of like, wait, actually, my bad. I think that this, like the checking thing, should happen before we remove the edge. Yeah, so we first check if the layover thing works, and then we take the edge out, and then we just run DFS over like our source, which is D, and then our time, which is S. And we also need to update our answer for D to be S. And yeah, so this is essentially how we run our recursion for DFS. And we initially call it from 0 with time -infinity, because otherwise, like, notice that 0 still has a layover time. So like the layover time for 1 is 10 right here. So, oh wait, not 0. Every time I said 0, I meant 1. So so 1 still has a layover time. So if we start 1 at like time step 0, then we're basically going to have to do some extra like lines of code to figure out like how to deal with the layover time, ignoring the layover time for this path specifically. And like it's doable, but like it's annoying. So we're not going to do that. So we instead start at DFS of 1, negative infinity. And that way we basically have to like just we can basically just ignore the layover time for the first pass, but if we revisit node 1, we still have to consider it, and we don't really need to do anything extra. And then initially our answer for 1 is just set to 0 because, well, we are there at time 0 already. So that is what it is. So anyways, yeah, this is essentially the solution for problem 3. Yeah, no, sorry for the small disruption with my roommate walking back and forth. My dorm is so tiny that even if we wanted to, there would be no privacy, so I gave up. Yeah, but are there any questions on how to do 3? All right, so I think that this sort of warrants like a bit of like a talk about when to use DFS and when to use BFS. So like there's like a for BFS, it all depends on like how you want to like go through the graph. So like for DFS is when we want to basically trace down like all specific paths. So for DFS, we essentially like start here and then we go to like this node and then we go here. So this has like, we're basically just tracing down each specific path in a certain order. And then for BFS, it's like if we wanted to do like shortest paths basically. So like that would be like essentially we don't really care what path we're taking as much. We just care about the length. We can still sort of recover our paths to get to each length, but like we don't really keep track of the order that we traverse them in. Dijkstra is like a BFS. First of all, it's like a BFS order algorithm. So any pitfall this question had with BFS, it also has with Dijkstra. Second of all, Dijkstra works as in we are like, I mean, it's sort of similar, but like not really. Dijkstra's is like we basically do like distance of u equals to like distance of v plus u, plus like the weight from v to u. Anytime we want to go from v to u. So assuming that it's better. So this is like not really the same because here what we're doing is essentially checking, okay, so what time have we reached a certain point at? And then we're basically still considering it even if it's not ideal because there is a chance that we could like time travel back to like a really good node from like a really late timestamp. So yeah, we're still going to end up considering that. So yeah, I don't think that BFS or Dijkstra are very good solutions for this problem. Any other questions? If not, then I will hand it back to Charlie.
Yes, thank you, Albert. I have a final slide to share with you here. If you may get your results by the end of this week, mostly Friday. If you pass, congratulations. If not, please don't be discouraged. Let's just keep up. Nothing is easy to be achieved if that's a big thing or significant things. So from XCamp, we will help you prepare the next USACO if you need to. First, we have March public USACO mock test. It's on March 18th, 4 to 8 p.m. Pacific time. The second one, we have summer on-site camp. It's the last 2 week of July. We based on San Jose. If you would like to improve more in the summer, please join our summer camp. We have limited seats, 20 students per level. Finally, you may know we have weekly weekend class. Our spring quarter starts April 1st. Summer quarter starts on June 21st. These are 10-week class online. Again, thank you all, Albert, again. Students, congratulations if you pass. If not, just keep up. Okay, have a good night. Bye.